Okay, so once again, I want to welcome you to our fourth lecture. This is the fourth day out of the 10 days. First, I want to congratulate you for having made it from day one to all the way to the fourth day, to the fourth lecture. And I believe you're picking a thing or two. So just like Cynthia said, she actually summarized everything that we last looked at in the previous lecture. We said previously that when it comes to networking or networking devices, we have quite a variety of them. And we also say that in addition to the traditional physical network, the networks for our virtualized environments also include some invisible networks which run inside those physical servers. So that's what we're trying to cover in this chapter. We looked at some of these objectives, and we said that upon completion of this module or chapter, we'll be able to understand some of the basic concepts of physical and virtual, how the virtual switches work, and also to understand the network architecture used in virtualized environments, and also to understand how the traffic flows between virtual machines, not forgetting the concepts related to virtual LANs or the virtual local area networks. So we are still, could you please hold on just briefly? Just excuse me just briefly. So we were saying, upon the completion of this, actually these are the contents, and we are looking at the network architecture for virtualization. We went ahead and we asked ourselves, how do virtual machines communicate, given the fact that they operate and run inside servers? So we wanted to know, if we have our server there and we have different virtual machines inside that server, how do they actually communicate with each other when there are absolutely no physical cables inside connecting them, or no physical switches inside connecting them? And we also came to realize that there are some invisible networking kind of environment and devices, or that are virtual inside the physical servers. So we went ahead and we talked about some kind of traffic that flows in virtualization. There's no much emphasis in the traditional network architecture, but when it comes to the network architecture for virtualization, we have two types of network traffic. Which one and which one? Could I get someone telling me? Just a volunteer, you could just say them out. The ones we talked about during the previous lecture, we said we had two kinds of traffic. So you mentioned them and you tell us, how do we determine that this one is this and this is that? Thank you.
We have
My sec.
All right, go ahead.
Yeah, we have the north east. We have the north-south network traffic. That one is determined through, it is determined by passing through the router. So if it passes through the router, that definitely becomes the north-south network traffic. Then we also have the east-west network traffic, and that one does not pass through the router. Thank you.
Okay. All right. Thank you, Ariho, for that submission. So we said we had north to south traffic, and also we said we have east-west traffic. And any traffic that traverses through a router is what we are calling or determining to be our north-south traffic. Okay. So we went ahead and saw some of these few concepts. We looked at what a broadcast is. We looked at the unicast routing, and also we looked at the default gateway, and we are also trying to look at the VLAN, and we are seeing it has some kind of different concepts here. And worry not, we are going to get into it. We're going to get into the details of the virtual or the the virtual local area network. So we looked at all those things. And at this time, we're now trying to look at what we're calling the virtual area network. And we are saying the virtual area network is the most common way to subdivide the physical local area network into separate logical broadcast domains. So the devices within the same virtual local area network can communicate with each other using their MAC addresses, which those in different virtual local area networks, they cannot. Okay, they actually are treated to be like they are in different kinds of networks. Therefore, broadcast packets can only be propagated only within one or the same virtual area network, but not across VLANs. Just like you see, if you have a network that maybe dot 1.2, 192.168.1.2, and you have another one of maybe dot 2 dot either 16, all these could be even zeros. So these are two different network segments in the physical, let's say in the physical area network. And once you send a broadcast packet, it is only propagated within one broadcast domain within this network segment. And this is the same thing that is also applying to our virtual kind of segment, because we are subdividing our physical network into logical networks. And some of our colleagues yesterday kept on hinting, yes, it is done for security purposes, but also it is also done to improve on the robust and performance of the network. Because imagine if you have so many devices connected on the same physical network, and whenever a broadcast has to be sent and it is sent across the same network, it is going to want to give a lot of work to the switches where those devices are connected. And then also you're going to have challenges, maybe if you are using RSTP, the rapid the spanning tree protocol, you're going to have issues. And that's why people or the architects decided to come up with this kind of technique, the virtual local area network, to help us subdivide this one huge gigantic network into logical. In physically, they could all be connected to the same switch per se, but now they're actually divided into different logical networks. Like the way you see this diagram just below here, you see we have one switch here and we have two switches. And these two switches, we can see here very well that we have a virtual LAN here, and we have a virtual LAN 2 here and virtual LAN 3 there. And we have another switch which also has virtual LAN 1, virtual LAN 2, virtual LAN 3. So technically speaking, this guy and this guy, they are on the same network, or they're in the same LAN, local area network. And then only the broadcasts that are sent from this virtual machine A, when you send out broadcast packets, they will only be propagated to the machines that are within the same virtual LAN, and that virtual machine B will be the only machine to receive those packets. And we see these guys are connected on the same switch, but we see they are on different virtual LANs. So this actually means that this person, to communicate to this virtual LAN, we shall need some kind of layer 3 devices, which will help us to trace the route, and we are able to send our packets to other networks, just like the way it happens in our physical network. So we are saying virtual LANs bring about these kinds of benefits to our network. One, it helps us to define broadcast domain, and each virtual LAN is a broadcast domain in a sense. And this helps us to save bandwidth and also to improve on our network throughput. It also hardens the local area network security, because packets from different virtual LANs, like I have illustrated here, packets from different virtual LANs are separately transmitted. They simply because they are connected to the same physical devices does not necessarily mean that they're going to actually be transmitted and this guy will receive a packet and maybe drop it if it is not the destination device. So we are saying it is going to also help us to harden our LAN security, and also at the same time it's going to help us improve our network robustness. It is going to a fault in one virtual LAN, like this virtual LAN 3 is faulty, it is not going to affect other hosts in other virtual LANs. The network will, in other virtual LANs will still be up and running as you fix now issues in virtual LAN 3. So the flexibly defines virtual work groups, and each virtual LAN defines a work group that contain users from different geolocations. So the beauty of virtual LANs is that actually we could be on the same network even if we are in different locations. We could actually be on the same network, like let's say the Stanbic network, they're on the same network much as we have a headquarter we have a branch in Jinja, a branch in Kampala, a branch in Gulu, Lila, and name it. So all those devices could actually be connected on the same virtual LAN. And we're saying this is some of the benefits that the virtual LAN brings to the network architecture. So the virtual LAN package is a traditional Ethernet data frame, and it has 4 bytes long. Just like the original data frame which is sent out from the data link layer. So this tag is, they add another type or segment of 4 bytes where they insert a tag. And this tag uniquely identifies a virtual LAN, a local area network, or a virtual LAN. So for us to be able to identify that this tag or this packet is either from the virtual LAN or it is not, it either has to be tagged or untagged. That's when we can actually find out. So whenever a tag comes on our network and it has that extra 4 bytes field, then we shall actually get to know that that packet is tagged and it is coming either from this virtual LAN and it is meant to go to the other virtual LAN. Okay, so we are saying here that the VLAN ID usually identifies the VLAN to which the switch belongs to. The tag has a VLAN as inside or part of that packet. We have the VID, or what we are calling the VLAN ID. We have our VID part of that packet frame. Usually our data packet looks something like this. You forgive my handwriting. Let me use maybe objects here to help me. Okay. All right. So we have our Ethernet frame here. We have our Ethernet frame, and previously on our Ethernet frame, we had, let me try and separate it. We had, on our Ethernet frame, we had our destination MAC address, okay? After our destination MAC address, we had our source MAC address, and all these were 6 bytes long. And of course, we had the length or the type of the packet just to help us determine which protocol is going to process this frame when it goes to layer 3. Is it going to be IP or IPv6, IPv6? And then after we have our data, which is always between 46 to 15,000 bytes. And also we have our frame checksum. So we are saying that here, I'm trying to see if there's a way I could type in properly, but it seems like I need to, okay, let me forget about typing. Okay, and I just draw. So we are saying that we had the default Ethernet frame. We have our destination address, we have our source address, and then we have our length or type, which is going to determine which next protocol should process this frame. We have our data, And then we have our frame checksum, which is going to check the integrity of the frame. So, and now when it comes to a tagged frame, the tagged frame is going to add another field which is 4 bytes long, which we are calling a tag. Let me just put it here. Let me use another color. Let me use blue. Let's say we are going to have another frame field part inside our frame, and this is going to be our tag, okay? The 802.1Q, or usually they just call it the tag field. So the tag field is 4 bytes long, and this tag field is now what we are actually used to identify where is this tag coming from. Is it either tagged or untagged? And we are saying inside this tag here now, we have our different fields, and one of those fields we have our VID, and this one we are saying that it is what we use to identify the VLAN to which the switch belongs to. Okay, so Ethernet frames can be divided into following types depending on whether they are tagged or whether they are untagged. So, like I've said, tagged frames are Ethernet frames with a 4 byte long tag, and untagged frames, they are the original Ethernet frames without that 4 byte tag field. So we are saying that although some operating systems and switch are both able to add VLAN tag to data frames, VLAN tags are usually added added or removed by the switch. Therefore, a VLAN has the following types of links, and we're going to look at them already. We have been seeing some of them included here. Am I recording? Yes, I'm recording. So one of the fields that we should look out for is the access link. Okay. One of the fields that we should look out for is the access link. And we are saying that the access link connects a host to a switch. We have our virtual machine here, or our host, or our physical host, and we are saying the access link connects the host to the switch. It is what we are calling the access link, okay? And generally, the host does not need to know which VLAN it belongs to, and the host hardware often cannot even identify the VLAN tagged frames. So therefore, the host can only receive or send untagged frames. Please take note. The host can only receive or send untagged frames. Take note of that. We are also seeing some other kind of link that is available. And we are seeing there's this link here. This is the access link. And we said, what does the access link do? A volunteer could just say it out, just briefly.
Hello. Connects
Yes.
the host to the switch.
Yes, it connects the host to the switch. And now we are seeing there's another link here, this one. And we're already seeing it is connecting what to what?
To switch.
Come again?
Switch to switch.
Switch to switch. Awesome. So we are saying that this one connects a switch to another switch or to a router, depending on what you're using. So that data of different VLANs is transmitted along a trunk link. So if you're having data of different VLANs, they are usually transmitted along the trunk link. So the two ends of trunk link must be able to distinguish frames with different virtual LAN tags. And I emphasize here and say that only tagged frames are transmitted along trunk links. Okay? Only tagged frames are transmitted along trunk links. All right. So those are the two types of links that we have when it comes to the virtual local area network. But then also we need to look at the interfaces, because the standard defines that the virtual LAN frame, only certain interfaces of a device can identify a frame based on their ability to identify virtual LAN frames. Interfaces are divided into two parts, okay? They're divided into two parts. And we are having what we are calling an access interface. We already know that the access connects the switch to the host, or the host to the switch, the link. We already know that the access link. Now we are looking at the access interface. And we are saying the access interface resides on the switch. Okay? It resides on the switch, and it is used to connect the interface to the interface of the host. So it resides on the switch, and it is used to connect to the interface of the host. Okay, the interface is where you plug the cable. Generally, just basically speaking, the link is actually that kind of, either that medium that is connecting the two devices. Okay, so do not confuse the links and the interfaces. So we are saying that it is used to connect the interface of the host, and this that is, the access interface can only connect the access link, and only packets carrying the default VLAN ID, take note, only packets carrying the default VLAN ID of this interface. So if the VLAN ID of this interface, let's say, is 1, the default one, only packets with the VID, we already said that the VID is used to determine the VLAN of that switch. So only the packets containing carrying the default VLAN ID of this interface can pass through. So if it comes and it is not of VLAN 1, we are going to see what will happen to it. And also, frames sent through an access interface do not carry any tag. So if the host here is sending, it does not send things that are tagged. It sends packets which are untagged. But we are saying that also only packets carrying the default VLAN ID of this interface are allowed to pass through. Okay, so let us also look at the trunk interface. We already know that the trunk link connects a switch to the switch, or even the router. And we are saying here that the trunk interface is used to connect a switch to other switches, and can connect only a trunk link, and a trunk interface permits tagged frames of multiple VLANs to pass through, because remember, it is connecting this. Someone is asking me what is LACP in full. That is a link aggregation control protocol. I don't know if they have asked here or via Telegram, but it's a link aggregation control protocol, and we're going to look at it shortly. But it is to bind different links together so that we can have more bandwidth. I'll explain it later. Okay, so and we are saying it is, these are the interfaces on the switch, but only you connect a trunk link, okay, to those interfaces, and they only permit tagged frames of multiple virtual LANs to pass through. This saying that now it will only, this interface here will only allow the tag of VLAN 1, VLAN 2, and VLAN 3. So if it comes and it's of VLAN 4, it will not allow it to pass through if it is not permitted to pass through on that interface. Okay, so interfaces of each type can be assigned with a default VLAN ID, and it is called the PVID, or what we are calling the port default VLAN ID. The meaning of default VLAN varies with interface type. So the default VLAN ID is almost all switches is 1. So we are saying here that if you are receiving or if you are receiving a packet which is not tagged, let us first look at that. Okay, so if we are okay, they're not talking about it later on. Okay, so we are saying here that if we are receiving a packet, let me clear that. So if we are receiving a packet on our access interface here, let's say on our access interface here. So if we are receiving a packet which is not untagged, what will happen? What will happen is that receive the packet and tag it with the default VLAN ID. So if this virtual machine is sending packets, remember for it, it sends untagged packets. And it comes to this one, which is a PVI, let's say 1, PVI D1. So it's going to receive it and then tag it with PVI 1, and then it will forward it. Okay? So strip the PVI tag from the frame and then send the frame. And let me see here. Okay, so that is what will happen. So let us look at when it is receiving a tagged frame. So when it is receiving a tagged packet, what will happen if our access thing is receiving a tagged packet? So if the VLAN ID of the tagged packet is the same as the PVI ID, the port VI ID of the interface, then receive the packet. So if the packet comes and it belongs to let's say VLAN 1, its PVID is 1, then it will go ahead and it will receive the packet. Otherwise, if it is, let's say 2 or 3 and it is not that of this interface, it will discard the packet. Okay? It will discard the packet. So what happens if a packet comes maybe from this guy of the same ID and they send it all the way here? What will happen? It will check. Is the VLAN ID of this packet the same as my port VI ID? Yes. Then go ahead and receive it. If maybe the packet is coming from this guy and it is not the same, it will ask itself, is it the same? No. Then discard it. So if it is the same and it is coming from this, what it will do, it will strip off now the PVID tag from the frame, and then it will send the frame to the host. Remember, we said the hosts only receive untagged, only send and receive untagged frames. So before it sends the frame to the host, then it will strip off the PVID and then it will send the frame. And this is the access interface. So if it receives a packet here which is untagged, what it will do, it will receive the packet and then it will tag it with the default PVI, which is of 1, and then send it. Then the packet will go, maybe it will come to this. Let me try and illustrate. This virtual machine here will send a packet to our access interface. Yes, Benya, your hand is up.
Hello. You said hosts only receive access traffic, right?
Yes, they only receive tags which will only receive packets which are not tagged.
Yeah, so let's just try to expound more on the practicality. If you have a server and then it's having, let's say, 10 instances, 10 VMs, and you're having sections, you're having 3 VLANs as you've put, I'm assuming all these are on one host.
Yes.
Does that mean that if you're connecting to an external switch, each VM, you bridge every a virtual NIC to an actual port on the server? You can't do it if the server has only one port.
You can't do it. No. Inside the server, there are what we are calling virtual switches. So these switches are actually not the network interface card of the machine. Let's say they're inside the server, and these switches here are now connecting to our network interface card.
So is there, so you, my concern is when you are setting up and
Yes.
you have, the server has only one interface, one physical NIC.
Yes, yes.
Is there a server that can accept trunk traffic, in that if I'm giving these instances different VLANs, that all those VLANs can pass through the one NIC on the server?
Yes, 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 true. You don't configure the PVI on the NIC of the server. You configure them on the port numbers of the switch, either virtual or on your physical switch, which you have in your network architecture.
Okay, yeah,
I want to
that I
say
get, but my concern was, you know, when you're doing before even the fact, before considering the VMs, most of these end devices have access ports.
Yes.
So I was just concerned about the possibility of these devices having trunk ports.
The port, you just configure it. You go.
Yes, that I get, but there are those which cannot do trunking.
There are those which cannot do trunking. Then one, that
Can I
switch
say
either has
something?
to be absolute, but most of the modern switches today, their ports give you an ability either to configure.
Not switches, but the end devices, the server itself,
No, that
more like the PC.
we already said the trunk is only configured. Have you been paying attention? The trunk
Can
only
I say something?
a switch to a switch or to a router. You're not connecting to the server.
I wish I could just draw what I'm trying. Kwesiga, you had something to
Okay,
say?
can we take that
Yes,
question?
I wanted to say something.
Yes, you can go ahead and say something, Kwesiga.
What he's saying, it's practical in this way. For instance, if the cable coming from the access switch to the server, it is he wants that cable, that server to be accessed by different networks. Let me say VLAN 1, VLAN 2, and VLAN 3.
Yes.
What he's explaining can be achieved in two ways. One, it's true that that port on the switch can be configured as a trunk, so that the cable connecting from that switch to the server, it's a trunk, but it should be also having untracked traffic, what in Cisco we call native VLAN ID, whereby the server itself will get the connection automatically, like the normal way, like an access port. Then the other traffic will be aggregated according to how he wants to split it in the virtual switches, the same way he's saying. It's very practical.
It's very practical. I agree. But could we please first continue, because it's going to make more sense later on. You don't necessarily have to configure that link to the server. You could actually, because for the traffic, we are going to see it as we go deeper and as we explain actually how this traffic is going to be moving. And I'm saying these could still be physical or they could still be virtual. So you can look at them in both ways, as either they are physical or they are virtual. And you can look at these things as either physical or virtual.
Okay.
Yes, but thank you so much for that submission.
All right.
All right. So, and we are saying, where were we? Okay, we are on the access, we are on the access interface. We are saying if a packet comes from this, let's say physical server here, and it is, you remember our hosts now send untagged frames, send and receive untagged frames. So when it sends it and this interface receives it, what will happen, it is that the access interface will tag it with a default VLAN ID, and then it sends the packet. If it is receiving it and it is having the same VLAN packet, PVID, then it will also receive the packet, but then it will strip off the PVID and then send the packet to where it is intended to go. And let's also look at the trunk interface. So if you're having a trunk interface here, or even there, and a packet comes in and it is untagged, what will happen, it will tag the packet with a default VLAN ID. And if the default VLAN ID is allowed on that interface, then it will receive the packet. What will happen also, it will tag the packet with default VLAN ID, and if the VLAN ID is not allowed on the interface, then it will discard the packet. So if this interface receives a packet, let's say from here or from any source, and it is not tagged, what will happen? It will tag it with a default. It will tag it with a default VLAN ID, and if that VLAN ID is allowed to go through that interface, then it will go ahead and it will send the packet. But if it is not, it will go ahead and receive the packet. But if it is not allowed on the packet, then it will discard the packet. Then let us also look at if it receives a tagged packet. So if it receives a tagged packet, if the VLAN ID is allowed on that interface, then it will of course receive the packet. But if the VLAN ID is not allowed on that packet, then it will go ahead and discard the packet. And then what happens after receiving it? Now it has to send it. If the VLAN ID is the same as that of the default VLAN ID and is allowed on the interface, then it will untag and then it will send the packet. If the VLAN ID is different from the default VLAN ID and is allowed on the interface, then keep it untagged, unchanged, then send the packet. So let me illustrate this animation of how sorry. Okay. All right, I think we shall look at it later. We are looking at the router. We already talked about the router. Could someone remind us what is a router?
A router is a layer 3 device.
Yes.
That interconnects networks, different networks, allows connection between different networks.
Okay. Yeah. Thank you. Who was that?
Triza.
Yes, thank you, Triza. Like she has said, it is a layer 3 device that connects computer networks, and also it is used to perform the traffic directing function, maybe on the internet or on different networks. Could you also tell us the difference between a layer 2 switch and a layer 3 switch?
A layer 2 switch basically just connects devices of the same network. That's layer 2. Devices that are on the same network, and it only does switching. Then layer 3 can do switching and at the same time can do what a router does. It can interconnect networks.
Thank you so much, Triza.
You're welcome.
All right. So we also see the network interface card, and you're all aware that all machines or computers have a network interface card. Could you also please tell us what a network interface card is? Or anyone who wants to participate? We looked at these devices yesterday, but just a recap.
I can try.
Yes, please go ahead.
A network interface card, this is the access port through which any machine is going to be connected through to the internet.
Okay, thank you for trying. So basically it is a component or a component. Yes, okay, go ahead.
Hello? A network
Can I try?
Yes, go ahead.
Is a hardware component. It's a hardware component that computers use to connect to a network. If a computer does not have a network interface card, it can't connect to the network. It's more of that hardware that connects them, connects a computer to the network.
Okay. Thank you. Thank you. All right. So you have said it all, and usually physical servers use their own physical NICs to connect to the network, and all virtual machine traffic enters the entire network through the different types of the ports, which then later on connect to our physical NIC, which is on our physical server. So how do router in a virtualized environment, when you send your traffic, it goes through our physical NIC of the computer, then goes through the router, and then to the internet. So that is just an illustration. And of course, also they're talking about here the different kind of traffic that we can have.
Service traffic storage.
Yes, please. Yes, please. You are saying something?
No, it was accidental.
Oh, it's okay. So in virtualization, applications run on virtual machines and virtual machines run on physical servers. So before connecting virtual machines to a network, you need to connect the physical servers to the network first. Okay, and usually to do this, you need maybe routers, you need layer 3 switches, layer 2 switches, and the physical server network interface card, which you have also looked at. And we also looked at the TCP IP. We looked at the TCP IP reference model yesterday, and you took us through the different layers of that reference model. And in cloud computing and virtualization, routers are usually deployed at the egress of an enterprise or institution to connect an intranet to the internet, to connect the local internet or local network to the internet. So when an intranet user intends to access the internet, the router will perform route forwarding and network address translation. So when an intranet user intends to access the intranet, the traffic will also pass through the router, depending on the kind of architecture that you have installed. So the router can allow the intranet to communicate with the internet, which means that one issue is addressed, that other issue is how to plan the intranet. So depending on how you want to plan, how you want to divide your traffic as a network engineer, so that you maximize on the bandwidth and the network throughput. So that will entirely depend on what.
Now,
Yes, please.
Kabaro.
Are you talking to me? So what happens is usually we usually divide the network traffic. Sometimes we can choose to have service traffic. We can choose to have service traffic. Where's my automation? We can choose to have service traffic. We can choose to have service traffic. We can also choose to have storage traffic, management, and service traffic, and then management traffic. And we can have different devices that are connected to our network. So service traffic and storage traffic are vital to the users, because usually users want to store something or access something which was stored. And also service stored, they want to access a service and maybe perform their duties on the network. So when users access a target service, then the service traffic is produced. So if service data is stored on a professional storage device instead of a local server, or like storage traffic then is produced. And when servers, or when a server and a storage devices, or a server accesses the storage devices, then storage traffic is now produced. So when user manages, when you are an operation and maintenance manager, when you manage servers and virtualization devices and storage devices, maybe change some configuration, maybe add some configurations, delete some, then management traffic is then produced. So service traffic and management traffic are carried on different physical lines depending on how the network engineer designed their architect. So if management traffic and service traffic are carried on the same physical channel, then this is in-band, or what they are calling in-band management service traffic. So in cloud computing, data center, a high-end layer 3 device is usually used as the core of the entire network during the design. So I'm just, if you get some time, you can also go and read through all that content, which is available in the learning material, but not so very much relevant to in terms of you getting prepared for the exam. But you can go ahead, and I advise you to go ahead and read through. It's an entire, like about 3, 4, 5 pages, just to go through them and read through them to have a better understanding. So this is also an illustration just showing you some of the things we're discussing or talking about, that usually on a server they access services and also store data somewhere, and different kinds of storage traffic is produced. Let me ask, if a user here wants to access something which was stored on this device, what kind of traffic is generated?
Storage.
It is storage. Okay. So, and if the user here wants to maybe make a posting, maybe it is a bank and they want to, you know, make a posting or post a transaction, what kind of traffic will be generated?
Service
traffic.
Service traffic. And if you now, you guys realize, they tell you that, you know what, one of the virtual machines is not performing well because maybe you allocated it less memory, and you now log into the physical servers. You log into the physical servers, and now you configure or change some of the settings, and also you go ahead and add it more extra storage. What kind of traffic will be generated?
management.
Management traffic. Okay, that is good. So a physical NICs in a virtualized environment. Okay, so a physical server, like we said, it uses its own physical NIC to connect to the network, and we said all virtual machines traffic enters the entire network through various types of network ports. Okay, so the NIC, the physical NIC, involves a key concept, which is port link aggregation. Okay, so the port aggregation indicates that multiple physical Ethernet links are bounded into one logical link to increase the link bandwidth, and in addition, the bundled links dynamically back up each other, greatly improving link reliability, depending on whether you choose to use manual or you choose to use the protocol itself, the LSCP protocol. Okay, so we are saying here that as the network scale expands, and you have, like our friend was telling us, you have like 6 virtual machines inside your physical server, users have increasingly high requirement on the bandwidth and reliability of the backbone link. So originally, to increase the bandwidth, users used high-speed devices to replace old devices, but this solution is costly and inflexible. So that's why where we introduce what we are calling link aggregation control protocol, which now allows multiple physical ports to be bounded into one logical port to increase the link bandwidth without upgrading the hardware. So the link backup mechanism of LSCP provides high link transmission reliability, and it has some of these advantages. Increased bandwidth, if you have already talked about it, because the maximum bandwidth of the link aggregation port reaches the total bandwidth of all the member ports, the ports that you have aggregated together. Of course, there's high reliability, since you can use one port as a backup to back up the rest of the ports. So if one active link fails, the traffic is switched to another available member link, thus improving reliability of the link aggregation port. Then load balancing, and in a link aggregation group, loads can be shared among member or active member links. So that is a link aggregation control protocol. As you can see, we have our physical NIC, and it is not bundled. The typical physical NIC, the NIC on your computer where you insert your Ethernet cable, and it is not bundled. So, but we can now have 1, 2 of them, and then we bundle them together to form one logical port, which is now also going to help us transmit everything, thus improving our bandwidth, increasing our bandwidth, and also increasing on the reliability. Let us look at the mainstream. Let us look at the mainstream virtual network architecture. What time is it? It is 8 past 6. Okay, so you can see here, we have our virtual machines. We have our virtual machines inside our host machine. We have virtual machine A, we have virtual machine B, we have our virtual machine C. Okay, and all these, they are somehow connecting to our physical machine. Now has 1, 2, 3, 4 physical NICs. But one thing we should also take note of this is that we have virtual NIC. We actually have 2 virtual NICs on these guest machines, all on our virtual machines. Okay. We also see some kind of switch here, which we are calling our virtual switch, which is inside our host machine. Are we together, team? And we have our guest operating system, and we have our libraries and applications and so on and so forth. So common virtualization systems usually use that kind of architecture, whether it is small or personal. Usually they use that kind of architecture. So virtual machines are bound to the physical NICs using sometimes it is either bridged mode or the NAT mode. Someone saying something? Okay, in a large scale corporation virtualization, virtual machines are connected to the physical NIC using virtual switches. The one that we are seeing here, we are seeing our virtual switch. So the network bridge, we all know the bridged mode, just like the way the hub works. The bridged mode is not a new technology, and you can use bridges to enable network ports to communicate with each other. Specifically, you can use network bridges to interconnect multiple network ports so that packets received on the network port will be replicated to the others. So what bridged mode does actually, it will connect like this cable of the virtual machine directly to the virtual machine all the way to our physical network without needing to translate or change anything. So in virtualization system, the operating system is responsible for interconnecting all the network ports. Like you see in this figure now, okay? The operating system, or in this case, the hypervisor, usually sometimes, depending on if it is type 1 or if it is type 2, the operating system is responsible for doing all that. So when it comes to MAC learning, the MAC bridge learns MAC addresses. Initially, the network bridge has no mapping between the MAC address and the port and sends data like a hub. However, when sending the data, the bridge learns the MAC address of the data packets and finds the corresponding ports using a mapping between MAC address and the CAM table. So what happens with this guy here, just know that what if you're using the bridged mode, the simplest way I can explain it, it will just mimic the state of your physical network interface card. Okay, so what happens to the port forwarding? So when we are sending each data packet, the network bridge contains its destination MAC address and such as its CAM table to determine the port through which the packet will be sent. So also in virtualization, each virtual machine has a virtual NIC. We have already seen these virtual NICs. A Linux operating system will generate a tap device in the user mode and the tap device driver and the NIC driver in the kernel mode. So data sent from the virtual machine will pass through the turn or tap character device file in the user mode. Okay, so basically it will come from to tap, and we are going to see the animation there, which will show us how that packet will be sent from there to there. So if only the bridge is used, virtual machines can communicate with internal networks using bridges. Okay, or NAT. So when a bridge is used, the bridge functions as a switch, and the virtual network interface card port is connected to the port of the switch. So if NAT is used, then the network bridge functions as the router, and the virtual NIC is connected to the port of the router. Could someone tell us what NAT means?
Before we go there,
Yes,
I have a question.
yes, please.
We have these 3 virtual machines.
Yes, please.
I'm wondering why are some of them connected to a virtual switch and another one is connecting to through here, then through the bridge and the NATing. And then I'm wondering what are those ports on the host machine that the virtual switch is connecting to, and the virtual machine A, what are those ports that they're connecting to?
Okay. When I was starting this topic, I said these are various ways how the virtual machine can connect to our outside network. This is a machine. This is an entire machine. Think of this as a physical server. And we are saying that a virtual machine or a physical server usually has what we are calling a network interface card. This is one. This is one here. This is another one here. This is another one here. This is another one here. Usually servers have more than 2 or more than 1. Usually our normal computers have one network interface card. So these are NICs. These are network interface cards. What did we say? What are network interface cards? Class, are we together?
It's the physical port that connects us to the rest of the network.
Yes, on a machine, the physical port where you put your Ethernet cable. Yes, so these are the physical network interface cards on our physical machine here. This is our physical machine. So we are saying that the virtual machines that we create inside our physical machine, they can either connect to our outside world through a bridge. Okay, before I even get there, when you create a virtual machine, we also, by default, they have actually a network card which is created for them, the VBR0, which is usually created by default with them depending on the architecture you're using. So a virtual machine has a network interface card, and this is virtual. Remember, it's not physical. Are we together?
Yes, we are.
Yes. So, and remember in the illustrations when we were beginning this chapter, we said one of the virtual machine can either have one or more network interface cards which you can create on it, isn't it?
Yeah, true.
Yes. So these are just now virtual network cards attached on this virtual machine of ours. These are network interface cards attached there. So we are saying, how do these virtual machines now communicate to the outside world in our network architecture and virtualization? We are saying they can either connect to our outside world using the bridged mode, where we have this network interface card connecting using the bridged mode to our physical network interface card. It could be this one, it could be that one, it could be that one. This is just an illustration. Okay? So it can connect using the bridged mode, which I was explaining before. Okay? And then it connects to, let's say we have our switch here. Let me draw some weird somewhere here. And then they connect to our
There is someone
switch
making
here.
noise in the background, please.
There's background noise. Okay, let me mute it. Okay. And now we are saying also, alongside all, apart from the bridged mode, still a virtual machine can access the entire network or the physical network through the network address translation mode, through NAT. Okay? And we're also saying that a virtual machine still, in a virtualized environment, we have virtual switches, and these are basically used more in enterprise networks, those big virtualized solutions. Usually, they connect to the outside world through a virtual switch. So what will happen, this virtual machine here will connect to our virtual switch, and think of this, it functions like our physical switch, layer 2 switch. And also this one will connect to our virtual switch. And remember, these are virtual network interface cards connecting to our virtual switch, which our virtual switch also now connects to our physical network interface cards. Okay. In the previous slide, we said we can actually even use LSCP to bundle these physical links together, all these ports together, the interfaces together, so that we can have actually increased bandwidth and also link reliability. And we can use link aggregation control protocol. So this is what they are also illustrating there. So it could even actually be one and they're not bundled together. Or we could even have another network interface card. We could also even have another network interface card here created. You just create it and add it there. And that network interface card also, we could as well as connect directly. We could as well as connect directly from our virtual machine to this, and also go ahead and connect. We don't have, yes, to this, and this will use these links to connect to our physical network interface cards, and so on and so forth. For you to create, I don't know if I started my virtual machine, I don't think so, but let me start it. In the meantime, for you to create a virtual network interface card, it's actually not hard. You just go in your virtual machine settings, create one, add one, put in the configurations you want, either choose whether NAT or bridged mode, configure it, and then you're good to go. And then you're good to go. Let me try and start my virtual machine. I'll come back to it later on. So ideally, who asked?
I asked.
Yes, Atriza. So ideally, this is just an illustration of the different ways of how the virtual machines can communicate with the physical or the physical network. I hope I've answered you.
Yes, you have.
All right. So I was asking, could someone tell us what NAT is?
NAT is network address translation.
And what does it do?
It helps translate IPs from one network to the other. If let's say from a public network to a private network, you don't want your private network IP to be known to the public, maybe to your ISP. So you use NAT to route another IP to the network.
Okay. Thank you so much for that submission. And that's why we are saying that when we use NAT in this scenario, the network bridge now functions as a router somewhere there. When a packet is sent here, it is going to be translated using the port number. And of course, it's going to be also sent to, and you don't need to have another IP address. What will happen if you're using bridged mode? You will have to assign, or this machine will actually have to get an IP address which is available on your physical network. But with network translation here, you could actually have a different network inside your virtual machine. Let's say you have your range of maybe .1, .0 to about, depending on what you want. And this, whenever the machines that are configured with these IP addresses, they are trying to communicate, this IP address is translated, and it will use the same IP address of that of the host. But what will happen, this will translate it, send it, the host will now access the internet or the outside world, and then when it comes back, still the NAT goes ahead and does the network translation. So when the virtual NIC is connected to the port of the switch, the virtual NIC and the network bridge within the same IP address configuration must communicate with each other in broadcast mode. That is just a brief overview. So NAT is used for address translation, and with NAT for address translation, when a virtual machine communicates with an external network through the NAT gateway, which is VBR0, in this diagram that you are seeing, the source IP address of the packet is translated into the IP address of that of the physical network bridge, and then it is this record is produced accordingly, and also when the packet comes back, it is also retransmitted back to that IP of that virtual machine. So this means that you actually don't need to buy so many IP addresses from your ISP, because you don't have to assign an IP address on the physical network to each machine if you're using NAT. But if you're using bridged mode, all these guys will need to actually be assigned an IP address that is in the pool or in the range of your physical network IP addresses. So NAT is widely used because when the IP address range of the physical network bridge has insufficient available IP addresses, a new IP address range can be added in your physical host. You can create your IP address range, but this IP address range now is translated whenever the packets are traversing from the guest machine to the physical network. So the source IP also can also be concealed. So people cannot trace the source IP of this machine because actually the network is now being translated and sent to the net gateway. Therefore, the external network will not know the IP address, thus protecting the virtual machine security. Okay, so the bridge and NAT are suitable for personal use or small scale use. So when the bridge is used, the status of the virtual machine or virtual NICs cannot be viewed, and the traffic on the virtual NICs cannot be monitored. So the bridge supports only GR tunnel with limited functions. For those who did routing and switching, you know what GR tunnel means. So the network bridge does not support software-defined networking, which is widely currently used in the modern networking architecture. So when it comes to large scale virtualization, usually virtual switches act as an upgrade network bridge, thus removing defects of the network bridge. And as we are seeing here, we have our virtual switch. So let me play this animation. When you're seeing, okay, the animation, yes, is here. So when you're seeing, this is a bridged mode. When a packet, I don't know if you're seeing this packet, it comes and goes as it comes and goes through our network bridge directly without changing the packet headers, without it being translated. Let me replay it again. When the packet comes here, it goes directly to our physical host without it being translated. But when it comes to our, you see there, the packet is now translated and our IP address is sent to our physical network with a translation on. And that is NAT and bridged mode. So let us look at the Open vSwitch. And we are saying the Open vSwitch, it has some of these advantages. Before I talk about it, security, it has a VLAN isolation, traffic filtering. We can also use it for monitoring. We can use the rapid span, we can use the S-flow and net flow, automated control through these different tools that are available, and of course, quality of services, of traffic queuing and traffic shaping. And we are saying that the OVS is an open source, high quality and multi-protocol virtual switch. It is developed by Nicra Networks using the open source architecture of Apache license protocol. And its main codes are portable C codes. So Open vSwitch is designed to enable massive network automation through programmatic extension and also support management interfaces and protocols such as the ones I have just mentioned down below. Okay, so there is, when you're using Open now, the virtual switch is here, the one we have just seen here. It uses that operating system. We all know that all switches have some kind of operating system that they use. And we are saying when it comes to virtualization, switches use some kind of operating system based on Open vSwitch, which has these different advantages or functionalities like we have seen there. Okay, so Open vSwitch has the following key components. Some of them we have showed them and highlighted them there. I'm going to skip them and refer you to go ahead and read some of them if you want to. But I want to focus on them in this lecture. What is the time? Okay, so I think we are going to go for a break for 15 minutes, for 20 minutes, and come back at exactly 6:50.
Hello.
Yes, please.
Yeah, I would request you share the attendance list because my data is about to get done.
Oh, so you're planning not to attend the next half of the class?
Not to attend, but in case it gets done.
Okay, don't worry. I'm going to share it, Maggie. No worries. Okay, so let me share the attendance list and kindly make sure that you register.
All right, thank you.
You're welcome. students of mine who did not do who are not doing an IT related course or who did not do IT. And we've been talking about routers, so I thought it important just to show them briefly. I don't know if you're able to see. I know it could not be clear, but this is yes, at a small scale, like personal, like in-house routers. This is how usually they look like. And you can also go ahead and Google and you try to find out more. This is for TP-Link, but those of Huawei or Swisscall, some of them look somehow different, depending also on the model and also the performance and capability of the device. So basically, this is a router, the one I'm holding. So as you see those diagrams, also you try to think about the image that you have just seen. And this is the physical cable for those who are not familiar. It's an Ethernet cable. This is, I think, Cat6E. It has a connection of RJ45. I don't know if you can be able to see. You could not be in position to see because I don't think the video is very clear. But those are some of the few physical devices. Some of the few physical devices that we have been talking about. All right. So let's continue with today's class. Someone wants us to put on face masks in okay. All right. So we're looking at we're looking at virtual switches, and also we looked at the OpenVS, which we said it's operating system that operates our virtual switches. Okay. See what's in the chat. All right. Finally, we get to see the face behind the main voice. Okay. So we were looking at the virtual switches, and we said a virtual switch can be a common virtual switch or a distributed virtual switch, the DVS. Someone was telling us before that what is a DVS? It's what we are calling a distributed virtual switch. So a common switch runs only on a single physical host, like these are other illustrations that you have been seeing. Let me maximize my screen here. Okay. So this is just a common virtual switch, but we are saying a common virtual switch runs only on a single physical host. And also all network configurations apply only to those virtual machines within that physical host. And that's why now some of us are now trying to say or think that what if we have our multiple virtual machines inside our physical server, but we also want them to access or use the different virtual LANs that are configured on our network? Do we have to configure the port to our physical server? But then we are saying that all the configurations apply to only the virtual machines on that physical hosts. And we're also looking at the distributed virtual switch. When you hear the word distributed, it means it is distributed. So distributed virtual switches are deployed on different physical hosts. Okay, so you can use virtualization management tool to configure distributed virtual switches in a unified manner. I repeat, you can use the virtualization management tool to configure distributed switches in a unified manner, and the distributed virtual switch is required for the VM live migration. So if you want to trigger high availability of VM migration, you will need to have configured the distributed virtual switch across your different machines. So we are seeing in this illustration here that actually we can have different machines. We have machine 1, machine 2, and machine 3, but they're all connected to one distributed virtual switch here, the one we are seeing here, to one distributed virtual switch, which is spanning across different physical hosts. So we can configure it, and we have different, let's say even VLANs and all that across different machines. And we see machine 1, and we have a virtual machine which is also connected to the distributed virtual machine, a virtual switch, which is spanning across host machine 1, host machine 2, and host machine 3. So in the Huawei distribution products, we use distributed virtual switches a lot, and that's why we were introducing you to the virtual switches, but mainly we are now going to focus on the distributed virtual switches. And we are seeing that distributed virtual switch, it spans across different hosts, and it can connect different virtual machines from different physical hosts. Okay. All right. So let us look at the network features of Huawei virtualization product. We have a Fusion Compute Network architecture. How does it look like? Okay. So Huawei distributed virtual switches can be centrally managed, and the centralized management module provide a unified portal for simplified configuration management and user management. Remember the unified portal we talked about of Fusion Compute, which you can access. So we are saying that the centralized management modules provide a unified portal for simplified configuration management and user management. And I repeat, please get this statement. Huawei distributed virtual switches can be centrally managed. Okay. All right. So virtual switches distributed on physical servers provide virtual machines with range of capabilities, including layer 2 connectivity, isolation, and quality of services. So usually multiple distributed virtual switches can be configured, and each distributed virtual switch can serve multiple CNA nodes in a cluster. Okay, I repeat, we can have multiple distributed virtual switches. We can configure them, and each one of these can serve multiple CNA nodes. We mean physical servers, can serve different physical servers in the same cluster. Like you see this illustration here, we can actually have this distributed virtual switch, the blue one, this blue thing here. Let me try to draw. We have this distributed virtual switch here, and it is serving multiple nodes in a cluster. We have our cluster there with machine 1 and machine 2, and we have this DVS which is serving them. Please take note of that. And also a distributed virtual switch provides several virtual switch ports with configurable attributes such as the rate, statistics, and etc. So ports with the same attributes are assigned to the same port number. I repeat, ports of the same attributes are assigned to the same port group for easy management. And ports that belong to the same port group are assigned the same VLAN. So if you're having a port group 300, or they all belong to port group 300, they actually belong to the same VLAN. Okay, so different physical ports can be configured for management plane, storage plane, and service plane. We already talked about what management plane and management traffic, storage plane and storage traffic, and service plane and service traffic. So an uplink port or an uplink port aggregation group can be configured for each DVSs to enable external communication of virtual machines served by different DVSs. So therefore, an uplink aggregation port comprises of multiple physical NICs working based on preconfined load balancing policies, like you see these ones. And in brief, I am trying to say that an uplink is a port which connects our physical network interface card to the interface of our distributed virtual switch. So an uplink connects or is a link between the physical NIC and the distributed virtual switch. So each virtual machine provides multiple virtual NICs, the VNICs or ports, which connect to different virtual switch ports of the switch in one-to-one mapping. Okay, so and a server allowing layer 2 migration in a cluster can be specified to create a virtual layer 2 network based on service requirements and a configured VLAN used by the network. So we have already seen in this diagram here, we have different port groups and different VLANs. And I am assuming my virtual machine here with its virtual NIC, it's virtual machine A, okay? This is virtual machine B. This is virtual machine C. This is virtual machine D, virtual machine E, and virtual machine F. So I am saying, if my virtual machine A wants to communicate with virtual machine F, what do you think will happen? Can I get a volunteer to say something? Anyone?
I have a thought on that. I think if virtual machine A needs to communicate with F,
yes,
they're both in the same VLAN.
Okay.
So I'm thinking they'll just use the virtual switch to do the communication without going physical.
Without going physical. But you realize that is true, yes, to some extent, but you realize this link actually does not exist. It is virtual. There's no any kind of cable connecting these two machines here. This is just this is a virtual machine spanning across these two machines. But you realize for these machines to communicate with each other, we need a physical device here.
Yeah.
Do you agree?
Yes.
So meaning for this virtual machine to be able to send traffic, it has to go through a physical device. Is that true? So meaning our traffic from here will come through our uplink to the physical NIC to our switch, and it will go and reach all the way to our VLAN 10 there. But there's no routing needed. Please take note of that. So if this guy sends packets, it will still be able to propagate and send the packets to this VLAN, the broadcast packets, because they all belong to the same broadcast domain. Okay? So in the same way, what will happen if this network interface card X wants to communicate with, if this virtual machine B wants to communicate with virtual machine C, what will happen? Trisha, could you still try? Is that-
Being in different VLANs, so need a router in there.
But remember, we configure port groups to belong to the same VLAN. And we are saying this network interface card of this virtual machine, this particular network interface card, we are configuring its port group to belong to VLAN 300. And also this virtual network interface card here, we are configuring its port group to belong to VLAN 300. So ideally, you are meaning they all belong to VLAN 300, isn't it?
How about the 200?
If you realize and you look critical, you look very closely to this diagram, it has two network interface cards. Do you realize that?
Yes.
With one network interface card configured with a port group of 200, therefore belonging to VLAN 200. And another network interface card configured to port group 300, therefore belonging to port 300. Do you get it now?
Yes, yes.
Yes. So meaning this virtual machine will be able to send traffic through this interface, through this network interface card to this virtual machine here because they belong to the same virtual area network of 300, same port group, same attributes. Okay? And also if this one needs now, this virtual, if this port with the port group 200 wants to send packets, it will have to send the packets through the uplink, through the virtual switch, and then they go all the way to our VLAN 200. We see some kind of bundling links together. What did we call this? Anyone?
Aggregation.
Come again?
Aggregation.
Aggregation?
LSTP.
Link?
Aggregation control protocol. Aggregation.
And why do we,
Link aggregation control protocol.
and why do we configure it?
More bandwidth, reliability, and yeah, more bandwidth reliability.
Okay.
So port bundle.
Yes. So let me play the animation here.
And load balancing.
Okay. So let me play the animation. So you see traffic that needs to go to this. This is, let me say this is A and this is B. And remember, this is our layer 3 switch. So meaning if this much as they are in the same physical machine, but if virtual machine A wants to communicate with virtual machine B, can you please hold up? Excuse me just a moment. Okay, so I'm back. Are we still there?
Yes.
All right.
Yeah.
Okay. I was saying that if virtual machine A needs to communicate with virtual machine B, the traffic has to be routed through a layer 3 device, a router or a layer 3 switch. Okay? for it to be able. And who could guess the reason why? Why is that so? Triza?
Why? What's the question?
For virtual machine A to be able to communicate with virtual machine B, the traffic, much as it is on the same physical host 1, machine 1, but the traffic has to be sent through a layer 3 device. Why do you think that is so?
Because they are belonging to different VLANs.
Yes, they are belonging to different networks or to the different broadcast domains. So therefore, these packets have to be routed to their destination. Okay, so let me also play the illustration, another illustration here. And you see now this one, it does not need to go through because they are both on the same port group, same VLAN. So it would actually send the packets directly to this virtual machine. And now if this virtual machine wants to communicate with this other virtual machine on host machine 2, it will have to send the packets through this layer 3 device, but they are not routed. It just sends them as packets are actually switching, and they are able to reach this host, let's say virtual machine, host machine 2 and virtual machine, let's say E. And that is how traffic flows in a virtualized environment. Okay, so let us try to look at what we are calling security groups.
I have a question.
Yes, please.
So all the DVS are always layer 2. There are no those which come with
Yes.
which are layer 3.
Yes. Virtual switches are typically layer 2 devices, and they perform functionalities of layer 2 devices. Thank you. So let us look at security groups. So users create security groups based on virtual machine requirements. As a cloud computing engineer, you sit down, think of those requirements, what traffic needs to access this virtual machine, what traffic has to go through this virtual machine, what should it contain, what shouldn't it contain, depending on the security requirements. So each security group provides a set of access policies. So basically, a security group is a set of access rule policies. So virtual machines that are added to a security group are protected by these access rules of the security group. Key things to note out here, that we come up with these groups, with these rules basing on the port groups. And VMs that are added to a security group are protected by the access rules of that security group. So users can add virtual machines to security groups for security isolation and access control when creating virtual machines. So as you're creating a virtual machine, you can either choose to add it to a security group for isolation and access control. And a security group is a logical group that consists of instances that have the same security protection requirements and trust each other in the region. So all virtual machine NICs in a security group communicate with each other by complying with a security group rules. So a virtual machine NIC can be added only to one security group. Kindly take note. We are saying that our virtual machine network interface card can be added to only one security group. Okay, so security group policies are similar functions as the firewall does, like the way how the firewall rolls out rules and sets rules and policies. They both use IP tables to filter packets for access control. So if you look at this illustration here, we have our role 1, role 2, role 3, and we are telling this virtual machine through using its network interface card, because we said one virtual machine NIC can be added to only one security group. So we are saying here that as it's trying to access or communicate with this virtual machine, it has to go through, actually it belongs to this security group, but it must fulfill the roles. So what happens if a packet is sent? When a packet is sent and machine A, rule 1 accepts it, it will go through. Rule 2 accepts it, it will go through. Rule 3 accepts it, and then finally the packet is delivered to machine B. So what will happen if machine A, this is our machine A, this is our virtual machine A, this is our virtual machine B. So what will happen when virtual machine B sends a packet and it doesn't meet a criteria or it does not fulfill the requirements of a given rule? So the packet will go to rule 1, it's accepted, go to rule 2, it is also accepted, go to rule 3, but if it doesn't meet that criteria, then that packet is discarded. So there will be no communication between virtual machine A and virtual machine B, simply because one of the rule is not permitted or does not meet the requirement of that rule. So sometimes we can use net filter, and net filter is a data filtering framework. So when processing the IP packets, it hooks 5 key points, these key points, and tries to match and see if this filter matches what you configured, and if the configuration is what is required of the rule, then it will either permit or deny it. So one thing you should take note out of these security groups is that it has a set of rules to give permission, and if all the conditions meet the configurations of that rule, it will be permitted and the packet will be forwarded. And it can have multiple rules. But if one of the rules is denied, then the packet will be discarded. So for example, if the packet is maybe, let's say if it is containing the IMCP protocol, deny it. Like let's say someone is trying to ping or trying to find out the route of the table, deny it. So if it comes here and that is a policy deny, or it could even be allowed. So it could either be deny or allow, depending on what you configure and as you're configuring the security group. Okay, so let us look at this quiz tonight. Which of the following falls into the category of north-south traffic? Could I get someone tell me? Laban, I see your hand is up. You want to say something? Or I first read out all the scenarios.
Hello.
Yes, Laban.
Did you just say that each VM NIC can be added to only one security group, or any VM NIC?
Only a VM NIC can be added to one security group. So you cannot have one virtual machine NIC belonging to two different security groups.
I'm getting you there.
All right, thank you. So let us look at this. Which of the following falls into the category of north-south traffic? We looked at north-south traffic. We are having traffic between virtual machines in a data center. We are having traffic generated when users access a data center through the internet, traffic generated during virtual machine live migration, traffic between virtual machines in different data centers. So, members, tell me, what do you think? I pick at random or I pick Precious? Precious.
Yes, Ssendi.
Yes, please, tell us. What do you think?
B. The answer is B. Traffic generated when users access the data center through the internet.
Precious is telling us that the traffic generated when users access a data center through the internet. Okay. All right. Anyone else with what
Yes.
different thought? Yes, yes, Michael.
May I choose A, B, and D?
You choose A, B, and D. Could you give us also reasons why you choose those ones, Michael?
Because in A, you will need routing in between. Also B, and then D also the same reason.
And also, you say A, B, and D?
D.
D, eh?
Yeah.
Okay. Ashraf, you want to say something?
Hello?
Yes, please. Go ahead and tell us.
I think the answer is B. Looking at A and D, that can be nullified if we have a layer 3 switch.
Okay, so Emmanuel says for him he thinks the answer is C.
Ssendi.
Sorry, yes.
B.
Yes, please.
Ssendi. Me, I can say B and D because the traffic is just going to the internet, and there might be a routing between the two data centers, which are just different networks. And B also just because uses a router or a routing protocol to connect the two networks within a data center, going outside or coming inside the data center.
So Precious says, makes an addition to his earlier answer, and he says for him, it is B and D, the traffic generated when users access a data center through the internet and also between different data centers. So let us try and use the elimination method, and we see if we shall arrive to the answers we want. We are saying here that which of the following falls into the category of north-south traffic. And we said for traffic to be qualified as north-south traffic is any traffic that has to traverse through a router. Okay? Just to traverse. Yes, please.
Also, there's a colleague who talked about layer 3. I think a layer 3 switch is a router by definition.
Yes, yes, yes.
Yeah,
But for
confuse router and layer 3 switch, they do the same thing.
But for the term north-south traffic, I don't think a layer 3 switch comes for the definition.
Okay, so let us try and we use our elimination method. So traffic between virtual machines in a data center. So we can have virtual machines communicating with each other in a data center without going through a router or even a layer 3 device. Agreed?
Agreed.
So it does not necessarily mean that whenever there's traffic between virtual machines and data center, it is north-south traffic. That is wrong. Like you already saw, we have our virtual machine, which you can have via our physical machine, which can have two virtual machines in a data center, and these virtual machines are communicating. Is that north and south traffic?
No.
So already, that answer is out of our options. Okay? Of course, there could be some funny network engineers who can design the architecture wrongly, and they use routers to connect. They use people are funny. People can choose to do things. In networking, all things are possible. So let us look at the option B. Traffic generated when users access data center through the internet. Is there a way you can access a data center through the internet without using a layer 3 device or a router? Is there any way you can do it?
No.
Yes.
No,
So
you
meaning
can't.
B is our answer. Is that it?
Yes.
Yes.
Okay, so let us also look at the option C.
To me, yes.
So Traffic generated during virtual machine live migration. Remember, live migration happens within a cluster, isn't it? Within a cluster of different hosts. So necessarily there can be traffic which does not require a layer 3 device. It just needs switching, isn't it? So this answer is also left out. Remove it from our options. Let us look at D. Traffic between virtual machines in different data centers. For example, you have a data center in Jinja, you have one in Nairobi, you have one in Rwanda. Is there any way, apart from other sophisticated means, which also will require you to have some kind of layer 3 device, that you can have traffic from these different data centers and accessing each other without needing a layer 3 device?
No.
So meaning it leaves us with our two answers of B and D. Agreed?
Yeah. Agreed.
Okay. So let us look at this question here. One virtual machine can have multiple virtual machines connecting it to different virtual switches. True or false? And give your reason why. True or false? True or false?
True.
True. Who is that?
True. Cynthia.
Cynthia. Yes, Cynthia. Why do you think it's true?
As we saw earlier, we saw that in an illustration you showed us, virtual machines had multiple virtual NICs connecting to different virtual switches.
We saw that we could have a virtual machine with different NICs connecting to virtual switches, isn't it?
Yes.
I think this card diagram just describes it. This one here, this machine has different virtual NICs and it's connecting to different virtual switches, isn't it?
Yes.
Yes.
So that makes our answer,
True.
true. Okay. So this chapter covers just the basic knowledge about physical and virtual networks used in virtualization environments. I also advise you to go and try, to interest yourselves in those things that we have mentioned, try to read more about some few things here and there. But right now you have all the knowledge you need to answer any Huawei related question when it comes to network basics used in virtualization. And this brings us to the end of this class, and I want to use the remaining few minutes to walk you through how to create a Huawei account, which we shall need later on to do that, to enable you to do the exam, and also for you to do some mock, which you will be doing later on. Okay, so thank you so much for being part of this class. So let me also take you through that segment which we are going to do. So I'm going to share. Someone is raising their hand. Laban, Friday, is everything okay? I see your hands are up.
Yeah, I have a question, sir. What actually determines a virtual machine to have either one or two virtual NICs?
It entirely depends on the requirements that you have as a network engineer.
I also have a question.
Does it depend on let's say the resources that you have on a physical server for a virtual machine actually to have one or two?
It doesn't depend on the physical server. Let me show you. Are you seeing my screen?
Yes. Yes.
Are you seeing? I have my network interface card here, my adapter here. Are you seeing it?
No, we are seeing the PowerPoint only.
Oh, sorry. I thought you have been seeing my screen. You are seeing it now.
Yes.
You are seeing it now?
Yes.
Are you seeing that guy here? There's no way I can make it bigger, so you'll bear with me, but let me try to highlight. This is my virtual network interface card with its details. And I can choose either what mode should it be? Should it be either bridged or should it be NAT or and other functionalities that are given to me by VMware. I can also go ahead and choose to give it the LAN segment I want, configure the IP addresses, and maybe give it a custom network for it to belong to. Okay. So, but me adding another VM, it doesn't configure. I already have one Wi-Fi interface card, my physical one. But it's just a matter of going to add, and the hardware wizard will come. This is my hypervisor helping me. I'll choose what I want to add. Is it a storage device? Is it a network card? So I want to add a virtual network card. So I select it and go to finish. And boom, it is added. This is the second one. I add another one, go there, choose what I want to add, and boom, it is there. Are you seeing them?
Yes. So without putting into consideration anything, you can add as more as you want.
It depends on what you want to achieve as a network architect. You don't just do it because you feel like you're interested in adding. For example, like the other previous illustration, if I want to have 2 port groups on the same machine, I'm going to create 2 network interface cards, virtual network interface card, assign one port group 100 and assign the other port group 300, just like this illustration here. Okay, this machine here that you're seeing, let me try to zoom in. Oops, sorry. This machine here that you're seeing, this virtual machine here that you're seeing, it has 2 network interface cards. Agreed?
Yes.
And one of them is belonging to port group of VLAN 200. So meaning this virtual machine can send traffic to the VLAN of 200, isn't it? And also another interface is assigned port group 300. So it entirely depends. Maybe the person who designed this architecture wanted this virtual machine to be able to communicate with this virtual machine. But also at the same time, he wanted this virtual machine to be able to communicate with this virtual machine without having to go through a layer 3 device, to be on the same network or the same broadcast domain. So that's why he had to configure 2 virtual NICs on this virtual machine, not because he felt like, let me just put all of them. So like I said, it entirely depends on what is the end result. What do you want to achieve?
I also have a question in the same line.
Yes, please.
According to the fusion compute, does it mean that every cluster will have its own distributed virtual switch, or every physical host will have its own distributed virtual switch?
We said you can have either one or more virtual switches in a cluster, isn't it? If it is just a switch within one physical host, then it is just a common switch. It becomes distributed when it actually spans across different hosts in a cluster. In a cluster, you could have 2 hosts, 5 hosts, 10 hosts, depending on your architecture.
So when can we have more than one distributed switch in a cluster? Like what can necessitate that? Can't one be enough?
One can be enough, and ideally, most of the times I've seen it is just one. But let's say if maybe all the ports are used up, I don't know, for some reason you feel like you want to have another, you can choose to have another, maybe for easy management, and maybe you have so many things already connected to one distributed virtual machine, and you want to have some kind of easy management, maybe that's when you choose to have another one, but I cannot answer that directly.
It's okay. It's okay.
All right, thank you.
I have
Hello,
a question.
I have a question.
Wow. Okay, Triza. Okay,
Now,
Triza.
when we have this virtual switch, number one, how is it created? You've shown how to create a network, a virtual network card, but is that the same process you follow to create the virtual switches? Then number two, how come in this diagram, one virtual switch is spanning across the different hosts? So where do you create this virtual switch that spans across different hosts? Yeah.
Okay, thank you. There was someone else with the question. Was it who else?
That was me.
Yes, please.
Mine relates somehow to the question that was asked about creating virtual NICs. Now, since only one virtual NIC can be added to only one security group, if I want my virtual machine to belong to more than one security group, does that mean I have to create other virtual NICs? Does it work? Is it feasible?
Yes, it can work. And if you want, maybe, but particularly that traffic that flows from that interface, because that port group, but it is feasible, you can actually be able to achieve that.
All right, thanks.
You're welcome. And then, Triza, yes, you can go ahead. We shall be seeing that when it comes to the practical bit, actually when we are operating Fusion Compute, so that you'll be able to see, because it's an enterprise virtualization solution. So we shall actually go through the processes. How do you configure? How do you create one? We shall be able to see that. How do you add data stores? This is just at the basic level of adding. Actually, this is just virtualization, but not in the sense of an enterprise level or large scale virtualization solution. So when we are actually playing with the Fusion Compute, I'll be able to take you through, and you'll be able to see how one can create a distributed virtual switch.
So can we now do assignment number 2?
Yes, you can. Very well. You can do it very well. So, I was saying, okay, let me first end this recording before I get into, I'm going to share this link with you. Let me end the recording just a moment.
Samuel, can I ask